All right, let's dive right in. I want you to think about something kind of mind bending. Could you add up an infinite number of things and get a finite answer? It sounds like a total paradox, right? But today, we're going to build the mathematical toolbox to solve that exact puzzle, starting with something called infinite series. Seriously, think about it. How can you just keep adding numbers together forever and ever and not have the sum just blow up to infinity? Well, this is the big question we're tackling. It's a puzzle that's captivated mathematicians for centuries, and we're about to get the tools to crack it. So it turns out every infinite series has one of two fates. It either converges, which means it hones in on one specific finite number, or it diverges, meaning it just grows and grows without any limit, heading straight for infinity. Our job, really, is to be detectives and figure out which path any given series is going to take. Okay, let's open up our toolbox. Our first major tool is called the integral test. And this thing is incredibly clever. It lets us build a bridge between the chunky, step-by-step world of infinite sums and the smooth, flowing world of curves and the area underneath them. Here's the big idea in a nutshell. Imagine the terms of our series are just the heights of a bunch of super skinny rectangles standing side by side. The integral test lets us compare the total area of all those infinite rectangles to the area under a nice, smooth curve that connects their tops. And the rule is simple. If the area under the curve is finite, our series converges. If the area under the curve is infinite, our series diverges. It's that direct a link. But hold on, you can't just use this awesome tool on any series you find. There's a critical safety checklist you have to run through first. The function you make from your series has to meet three conditions. It's got to be positive, it's got to be continuous, and, eventually at least, it has to be decreasing. If you can check all three of those boxes, you are good to go. Okay, theory is one thing, but let's actually get our hands dirty. We're going to grab a real series and put the integral test through its paces, step by step. So here's our test subject for today. The sum, from 1 to infinity, of n divided by n squared plus 1. Now, just by looking at it, who knows? It's not obvious at all if this thing is going to converge or diverge. So let's bring in our tool. First things first, we have to turn this series, which is made of discrete terms for whole numbers n, into a continuous function that works for any positive number x. And it's super easy. You literally just replace every n you see with an x. That's it. All right, time for our checklist. For any x that's 1 or bigger, our function is definitely positive and it's definitely continuous. So boom, 2 boxes checked right away. But the big question, the one we really have to investigate is this function eventually decreasing? Does it start heading downhill? And how do we prove, without a doubt, that a function is decreasing? That's where calculus comes in. We just need to find the function's derivative. Because remember, if the derivative is negative, it means the slope of our original function is negative, which means it's heading downhill. And when we run the numbers, we find that for any x greater than 1, that derivative is negative. So yes, it is decreasing. That's the final check mark on our list. All conditions have been met. We have the green light to finally use the test. And now, for the main event, we set up the integral of our function from 1 all the way to infinity to find the total area under that curve. And when we solve it, what do we find? The area is infinite. And this right here is the magic of the integral test. The verdict for the integral is the exact same verdict for the series. Because the area under our curve blew up to infinity, we now know with 100% certainty that our original series also diverges. It, too, heads off to infinity. Problem solved. Now, the integral test is amazing and powerful, but let's be real. That was a fair bit of work. So what if I told you that for a very common, very special type of series, there's an incredible shortcut? It's time to meet the p-series. Think of it as a much, much faster way to get the right answer. So this is a p-series. Its form is super specific and really easy to spot. It's always the sum of 1 over n raised to some constant power, which we call p. And that little number p up in the exponent, that is the only thing we need to care about. I mean, just look at the difference here. For the integral test, we had to define a function, we had to check 3 different conditions, and then we had to solve a tricky improper integral. For a p-series, you just look at one number, that exponent p. That's it. It's a game changer. And here is the whole rule in all its beautiful simplicity. If the exponent p is strictly greater than 1, the series converges, period.
If p is between 0 and 1, and this includes being exactly 1, the series diverges. That's it. It's one of the cleanest, most direct tests in all of series mathematics.
A perfect and really famous example of this is the harmonic series. That's just 1 plus a half plus a third plus a fourth, and on forever. You can see this is a p-series where p is exactly 1. And our rule tells us that when p equals 1, the series has to diverge. Which is so weird, right? The pieces you're adding get smaller and smaller, but the total sum still goes to infinity.
Okay, let's really hammer this home with a quick side-by-side comparison. This is going to make that p-series rule absolutely crystal clear.
Check this out. On the top line, we've got our harmonic series, the sum of 1 over n. We immediately spot that p equals 1. Our rule says if p is less than or equal to 1, it diverges. Done. Now look at the bottom line, the sum of 1 over n squared. Here, p is 2, and since 2 is greater than 1, our rule says it converges. Instant answers, no calculus required. So, what's the big takeaway from all this? Well, the integral test is our foundational tool. It's the workhorse that gives us the deep, graphical reason why a series does what it does. The p-series test, on the other hand, is like a specialized power tool. It's an incredibly efficient shortcut that gives us the answer in seconds, but only for that specific family of series. It's all about knowing which tool to use for the job. Okay, so we've got a powerful, all-purpose tool and an elegant, lightning-fast shortcut. But this just brings up a new question, doesn't it? What happens when a series looks a lot like a p-series, but it isn't a perfect match? What tool do we use then? Well, for that, our toolbox needs a few more instruments, like the comparison tests. And that's a story for our next explainer.